going to demonstrate how a floating bottle will demonstrate a simple harmonic motion. So if I, for example, right now, if this bottle is floating in equilibrium, you can see that it's actually going up and down. It's going up and down. So if I put this mass, if I put this bottle a little bit into the water, so the upthrust or the buoyant force is greater than weight. But the buoyant force is directly proportional to the displacement. For example, how much you displace this bottle. So this could demonstrate a simple harmonic motion. So by measure the period, I can verify whether this floating bottle behaves like a simple harmonic motion. Let's quick explain why a floating bottle display a simple harmonic motion. So when this bottle is floating in equilibrium, the weight and the upthrust or buoyant force are exactly equal in magnitude and opposite in direction. So if this bottle is displaced at delta x into water, now this upthrust or the net force equals to density of the liquid times g times the volume displaced. But because this is cylinder, so the volume displaced should equals to the cross-section area of this bottle times the amount of length that is displaced by the bottle. Now I can write down the net force, which is upthrust force, equals to negative rho GA delta x. So the negative indicating that, so when the displacement is going down, the upthrust force is going up. So the net force is up. So the net force and displacement are in opposite direction. So upthrust force, now this providing net force equals mass times acceleration equals to negative rho GA delta x. So I get this acceleration. And finally, because this exhibits features of simple harmonic motion, so I can write omega squared should equals to rho GA divided by m. And finally, I get this equation. So period T should equal to 2 pi square root m. M is the mass of the bottle divided by rho, which is the density of liquid, in this case water, times G, which is 9.81, divided by A, which is cross-section area of the bottle. So in this case, the diameter of the bottle can be measured by using a vernier caliper, and also the mass can be measured using the balance, and density is known of the density of the water, and that's the period. That's the prediction of the period. Next, you can see that right now the bottle is already filled with some sand already. So now I'm going to raise this bottle a little bit, so allow it to oscillate up and down. So there's quite a lot of swinging already. So let's try again. Now let's do it gently. Okay, 3, 2, 1. Okay, now I can using a stopwatch to measure the period. So this is a prediction, which is 0.77 seconds. That's the real values that I measure with my stopwatch, which is 0.83 seconds. Well, that's a 10% difference already. So students should be able to identify what kind of problems that's causing this deviation from this prediction. I think the one we can observe from this floating bottle is actually there's some water actually getting stick to the bottle. So the water is actually adding some mass to the bottle, so that total mass actually getting larger. So if the mass is getting larger, so the period is getting longer. So that's one reason. The second reason is, well, as you can see, there's a significant damping. So the assumption needs to be challenged, because the net force is not just upthrust in this case, and the net force can also be drag force. So to improve this experiment, so the students should perform at least 6 more trials. For example, by changing the mass and measure the period again, and measure it again, and measure it again. Obviously, the measurement of period is the most challenging because of the damping effect, because the damping, so that the oscillation could die away pretty quickly.